We all know that attentions are important, but to be honest, this is one of the first papers that introduced attention, and this was for images. And let's try to go through that. You're going to show an image, you're going to attend to the part of the image that are relevant, and then you're going to talk about them. You're going to generate a caption. For the encoder, you want to generate captions. So your captions are sequences of length C. So I'm just introducing notation. Each YI here is a one of K encoded word. K is the size of your vocabulary. C is the length of the caption. A, you take an image and then turn it into a set of feature vectors using a CNN. So this is going to become more clear if I give you an example. Let's take an image, and that image is going to be 256 by 256. These are the number of pixels, the height and the width of your image, and it's going to have 3 channels. So each image is a tensor. It is going to be 256 by 256 and 3. You take an image, and then you push it through a bunch of CNN layers, and in the end, you're going to get another image. So an image goes in, and another image is going to come out of your convolutional neural networks. So what's going to happen? You're reducing the number of pixels in the end. It's going to be 14 by 14. And then you're going to have, rather than 3 features, you're going to have 512 features. So an image goes in, another image is going to come out. So that's another image. So what is cool now, the pixels in this new image, they are going to be 512 dimensional. So D here is 512. L, you can take those pixels and then you can concatenate them. You can turn them into a vector. Basically, you flatten it. And then that's going to give you 196 vectors. And this is your L. So this is your set that you're going to end up with. An image goes in and you're going to get a set of vectors. But what is cool here, the pixel sitting at location 2 and 5 of this feature map, it is 1 pixel at this layer, but it's going to correspond to multiple pixels on the original image. Okay. And that is going to be called a receptive field. Each one of these is going to correspond to multiple pixels. A big portion of your image is getting summarized into 1 pixel at this location. So is everything clear up until this point? An image goes in, another image is going to come out. Perfect. We all know about the soft attention, what you saw. Now I'm going to explain the hard attention. This was the first attention that was introduced. What is the stochastic attention? You want to know how much attention to pay to this pixel AI, how much attention to pay to each one of these pixels at the feature map at the last layer of your convolution. What you can do is you can multiply them by a bunch of numbers. And previously, these were deterministic. You had an attention span of 1, and you would span it across these vectors. Now, what are we going to do now? This is going to be a random variable. It's going to have a distribution of its own, and then we're going to model the distribution. A better notation here would have been z hat of t is equal to the summation of sti ai, but let's stick to the notation of the paper. What is st? It's a random variable, and this is going to be 1 if you are paying attention to location I. So sti is going to be 1 if you're paying attention to location I, and it's going to be 0 otherwise. So now you're going to see, you're seeing why this is a hard attention. You generate a random vector S. Most of the times it's 0, and sometimes it is 1. At a single location, it's going to be 1, and z hat is going to be ai. So this is hard attention. Okay, let's model this distribution. If sti is supposed to be 1 at a location, you can model that probability by a bunch of alphas. So this is going to give you the probability of sti being 1 at that location, at location I. And this is going to give you a vector. Per each time, you're going to have a vector. You're going to have, and this is the element of your vector. If you put everything in one vector, it's going to give you alpha t. And then we know that because it's a probability, it has to add up to 1. So you're going to use your softmax on a vector. And this vector you need to model. And we are going to model that like we were modeling it before, using it's going to give us the scores. and we're going to use a usual multi-layer perceptron. So it's fully connected neural network with some nonlinearity. So think of A as your image, and think of H as the hidden state of an underlying LSTM, because we are processing sentences. Okay, so there is going to be an underlying LSTM. The objective here is not to go into details of the LSTM, but rather this attention mechanism. So this is a hard attention. According to this distribution, you're going to sample one S, and that S is going to be 1 at a particular location and 0 everywhere else. And therefore, you're paying a hard attention to that portion of your image. Now, the question is how we're going to model. In the end, we are not interested in S. We are interested in the probability or the log probability of the sentence, of the caption, given the image. That's what we are interested in the end. It means that because S is a stochastic variable, it's a random variable, we need to marginalize it out. So we are going to have to integrate it out. And that's exactly what we are going to do. You have a log. Think of this as your integration. And then you're integrating out S. You're integrating over S. You're integrating it out. You have P of Y given S and A. S is your attention. A is your image. Y is your caption. If I know the attention, if I know the image, I'm going to be able to produce the caption. And then for each image, you're going to have the corresponding attention. There's going to be a distribution on that, distribution on the attention given the image. Okay, perfect. So you're going to marginalize this out. So you guys know that the log of a product is going to give you the summation of a bunch of logs. That we know. We have been using this forever. But what you didn't know is that the log of the summation, it is definitely not equal to the summation of logs. So that's not going to happen. There is this Jensen's inequality, which says that the log of an integral is the integral of the log. So it's bigger than or equal to the integral of the log. And this summation, in addition to this probability, you can think of that expectation. So you're taking an expectation with respect to S. So log of the expectation is bigger than or equal to the expectation of the log, because log is a concave function. So that's what the Jensen's inequality is going to tell us. Okay, we're going to use that. Rather than maximizing this, because we couldn't compute it, this was a hard formula to compute, we are going to compute L. It is easier to compute, and I'm going to tell you why it is easier to compute. And then you're going to maximize L. If you maximize L of S, you're going to maximize your likelihood. If you push this part up, the other part should go up as well. So we want to maximize this. And whenever you want to maximize, you're going to do gradient ascent. You need your gradients. Let's take the gradients of your lower bound with respect to the parameters of our model. So each one of these probabilities are going to be parameterized using an LSTM and using this attention mechanism and using the parameters of our CNN. So there are going to be some parameters. Okay, let's take derivatives. The derivative of L with respect to W, there is a summation here. It's going to be the summation of this P and the gradient of this log with respect to W. So that's the first term, plus this other term times the gradient of P with respect to W. And there is this nice trick that I want you guys to learn about. We know that what you need is going to be log of this and the gradient of P. That's the term that we are looking for, but here you don't have it. You have this complicated looking P of P times log times the gradient of the log. Let's see what happens. Let's take the gradient of the log with respect to W. What do you get? You get the gradient of P with respect to W divided by P, because the derivative of log is 1 over P. Derivative of log of Z is going to be 1 over Z. So that's just the derivative of log. Okay, you get the gradient of P with respect to W in the numerator. In the denominator, you have P. P here is going to cancel with this P here, and then you get exactly what you needed. You have log of P times the gradient of P. So why did we do that? Why are we doing this? Because now you can think of this term here as expectation. It is the expectation of some term. And now you can use Monte Carlo. You can generate samples from S. we can turn this integral or this expectation into a summation. Now you have some samples from this hard distribution. If you remember, this has a distribution, so you're going to keep sampling from it. And that's the term that you have. So is everything clear so far? So why am I going through this math? Because we are building our way towards reinforcement learning as well. And this trick, you're going to see that over and over again. The derivative of the log, you can relate it to the derivative of the numerator divided by divided by the argument. And we're going to use that over and over again. So is everything clear? Okay, perfect. So we're going to do Monte Carlo estimation. And then this is the gradient that we need. This is an estimate of the gradient. And what are these SNs? You're going to keep sampling from this multinomial distribution that you just created. So you're going to sample from that. So there is a question about this hard attention. We are introducing a random variable that is going to be 1 or 0. It's going to be 1 at location I, and it's going to be 0 everywhere else. What happens if this attention is going to be hard because you're paying attention to only one portion of your image, to the portion that corresponds to AI. And you have a distribution on S. It's a random variable. You can sample from it. And exactly here, you're sampling from it. Does that answer your question? And then I'm going to compare this to the previous attention that we know of, to the soft attention, shortly. So we're going to get there today. Okay. But if you want to properly model attention, this is how you're going to model it. You're going to put a random variable here. Sometimes it is 1. Most of the times it is 0. And then you're paying attention to one portion of your image while predicting the text. So this is Monte Carlo. There's a problem with that. This is going to be an unbiased estimate. This right-hand side is an unbiased estimate of your gradients. So it's a good estimate. It's unbiased. Its expected value is equal to the actual number that you're interested in, to the actual derivative. But there is a catch. It has a huge variance. So it's going to oscillate a lot. When you keep sampling from this multi-nully distribution, it's going to sample a lot. To reduce the variance, there is this trick that you can subtract a number from this log of p and then play around with the variance and try to reduce it. So you can use this is a moving average of these log terms. So it's a moving average of these logs. So you're going to subtract the average from this term. And this is a moving average. It's going to be your baseline, and then you're measuring your deviations from the average. Okay? And then don't worry about this entropy for a second. We have these terms here. There is a summation, the log part we didn't touch. We are going to subtract the baseline from this log term here. So we're going to subtract the baseline from here. That's the expected value of those terms. And then you can have an additional hyperparameter. This could be 1. Mathematically, this should be 1. But you can put a parameter there and then play around with its value. You can use some validation data and set this. So this is a hyperparameter. And then the rest of it is the same as before. So what you're doing is just subtracting the mean from these values. So these are just oscillations around the mean that you're taking into account. It turns out that this estimator is still unbiased and it has a lower variance. And there is another catch for reinforcement learning. So this is very close to reinforcement learning. You want your agent to be able to explore and at the same time exploit. So it has to balance the trade-off between exploiting and exploring. The entropy, if you add it, it's going to help your method explore more. So it's going to help it sample more diverse samples from the multi-nully distribution. So you're just increasing the entropy of your samples. This is exactly the algorithm that they call reinforce. So it's a very simple algorithm. It's from a very long time ago. And this is exactly what you're going to do. These are exact details of that algorithm. And one of the reasons I went through this paper is because of this. So one step was to reduce the variance. The other step is to help your method generate more diverse samples. So explore more. And this is going to give you the estimates of the gradients that you need. Now that you know the gradients, you can do gradient ascent while updating the parameters W. You're going to maximize L of S. And if you maximize L, because your likelihood should be bigger than L, bigger than the lower bound, your likelihood is going to go up as well. So you're maximizing your likelihood. And all of this trouble was because you needed to marginalize S out. You couldn't compute the likelihood anymore because it is complicated. There are some random variables going around in there. How does it relate to deterministic soft attention? Let's take the expected value of this random variable with respect to our distribution. So the expected value of z hat. There is going to be a summation. The expected value of the summation is the summation of the expected values. Expectation is a linear operation. This is just a constant, and it's going to be the expected value of S, and the expected value of S, the multi-Newly distribution, is going to be these alphas, the probabilities. So that's the expected value. So you're going to make an approximation here. You're going to say, forget about these being a random variable, just set z hat of t to be alpha ti ai. And this guy, you know, this attention, you know, they're going to add up to 1. You have a budget of 1. There's a softmax here, and then you're spreading that budget of 1 among your input. So this is an approximation of what you do with hard attention. Don't worry about this beta term. This is reducing the attention a little bit because these are images, and without this, the method wouldn't converge. There is another trick that we know that if you do a summation over I, these are gonna add up to 1. This is the budget that you had. So this is bounded in terms of i's, but then there is no bound if you do a summation over the sequence length. If you do your summation over t, there is no bound. You can make that bounded by setting a hyperparameter here, tau. It's some number that you choose, and then you penalize that in your loss function. You say that with some penalty, I want this summation to be around tau. So now you're penalizing that. And this was needed because without this, the method wouldn't converge. Okay. And the reason for that was because these are unbounded. They could get unbounded. The decoder, so far we were talking about the encoder. The decoder is when you are predicting the caption. It's actually when you're generating your caption. The decoder is an LSTM, input gate, forget gate, output gate, cell, memory cell, and then hidden state. And then you're paying attention. So z hat t is exactly what you have. It could come from the soft attention, or it could come from the hard attention. And we know that whenever you're predicting words, you're gonna have a softmax. So you're dividing by some normalizing term here to turn these numbers into probabilities, but this is gonna be related to this exponential term. And there is also some attention there going on. Is your embedding matrix. And then how do you initialize your decoder? How do you initialize C0 and H0? You're gonna initialize them using 2 neural networks and the average image that you're seeing. So you're averaging across all of these 14 by 14 numbers, across 196 numbers, vectors actually. I know this was tough, but let's look at some figures. The soft attention, while predicting a bird, is going to pay attention in a soft manner to the bird, and the hard attention is going to pay attention in a hard manner. So it's going to pay attention to one portion of your image. And this is the soft attention. If your sentence caption, the output caption is a stop sign is on a road with a mountain in the background, and if you focus on stop, you're going to notice that your method is focusing on the stop sign. And if you want your method to focus on the trees, or if you want to check it, whether it's focusing on the correct thing, you can see that it's focusing on the correct thing. So it's focusing on the trees. Okay, any questions?
Why would you want to use hard attention? Because it seems like if its expectation is just soft attention, then instead of sampling, I should just compute its expectation exactly and use soft attention instead.
So you're losing a lot of your statistics. So the proper way of doing it is this hard attention, but it turns out that they're going to give you the same performance. Why did I go through this? Because I wanted you to see that the proper way of doing it is using hard attention. The soft attention is an approximation to the hard attention. It is nicer. It looks nicer. Mathematically, it's easier. And the other reason I went through this is because I wanted you to see reinforce. And I want you to see this trick with the derivative of the log of the probability. So for multiple reasons, I went through this paper, and this is an amazing paper. Okay, does that answer your question?
Yes, thanks.
I guess I'm going to stop here. For those of you who want to leave, you can leave. And the ones who want to stay and ask questions, I'll be around.
I had a question about the energy for the Markov random field in the previous paper.
Okay. So do you see my screen?
Yes. I guess intuitively, I'm just thinking about here it says we're minimizing this energy. And in this case, it seems more intuitive to me that we want to maximize something which is, our alignment scores are high and we have consecutive words assigned to the same image region. So it feels more intuitive that there should be a maximization. Is there like a minus sign missing, or like, I guess, where's my intuition wrong here?
I guess you're right. So there should be a minus here. So yes, you want to maximize the assignment between these two.
Okay, that's my only question. So if there's, so instead it would just be min A, and then there's a minus of this E.
Yes, and you're right. You want to find a maximum assignment between these two.
All right, cool. All right, thank you. That was my only question.
Sure.
All right, have a good weekend.
You too. Bye.